In this video, you will learn how to measure the height of tall objects that are impossible to reach, like a flagpole or a building, using only a stick and the power of shadows. Our learning objectives are to understand the geometric principles of Thales' theorem and apply the concept of similar triangles to real-world measurements. Our specific goal is to use the ratio of a known object's shadow to find the height of an unknown object. Imagine you are standing outside on a sunny day. The sun is so far away that its light rays hit the earth at the exact same angle for everything in your immediate area. Because these rays are parallel, the objects and their shadows form two triangles that have the exact same shape, just different sizes. In geometry, we call these similar triangles. To understand why this works, let's look at the geometry. The sun's rays create similar triangles. The angle of elevation is constant. Because the sun is at the same position in the sky for both objects, the angle of the sun's rays is identical. Since both the flagpole and the stick are perpendicular to the ground, they both form 90-degree angles. If two triangles have two angles that are the same, the third angle must also be the same. This means the triangles are mathematically similar. When triangles are similar, the ratios of their corresponding sides are equal. This is the heart of Thales' theorem. Big height over big shadow equals small height over small shadow. In other words, the ratio of the flagpole's height to its shadow length is exactly the same as the ratio of the stick's height to its shadow length. Now, let's walk through a real-world example step by step. Suppose you want to measure a tall flagpole, but you don't have a ladder. All you have is a meter stick and a measuring tape. First, we measure our reference object. We know the height of our stick, lowercase h, is exactly 1 meter. Next, we use our tape measure to find the length of the stick's shadow on the ground. Let's say lowercase s is 1.5 meters. Finally, we measure the long shadow cast by the flagpole. We find that uppercase S is 9 meters. Notice that we now have 3 known values and only one unknown, the actual height of the flagpole. Take a moment to look at these numbers. If a 1-meter stick casts a 1.5 meter shadow, do you expect the flagpole to be taller or shorter than its 9-meter shadow? Now let's use algebra to find our answer. We start with our proportion from Thales' theorem. The height of the flagpole divided by its shadow equals the height of the stick divided by its shadow. Let's plug in our known values. To solve for capital H, we need to isolate it. We can do this by multiplying both sides of the equation by 9. Now let's simplify that fraction. 1 divided by 1.5 is the same as 2/3. 2/3 of 9 is 6. So the flagpole is 6 meters tall. Notice how we found a height that was impossible to measure directly just by using a simple ratio. This works because the ratio of height to shadow is a constant property for any vertical object at that specific time of day. To wrap up, let's review the simple 3-step process you can use anywhere. First, find a stick or a person of a known height and measure the shadow it casts. Second, measure the shadow of the tall object you are curious about. Finally, multiply the tall shadow by the ratio of the small height over the small shadow. This method was used by the ancient Greek mathematician Thales to calculate the height of the Great Pyramid of Giza over 2,000 years ago. It remains one of the most elegant examples of how simple geometry can solve massive real-world problems. Next time you're outside on a sunny day, try it yourself. Just remember, the ground needs to be flat for the shadows to be accurate. Now you have the tools to measure the world around you using nothing but the sun and a bit of math.